Hello everyone, welcome to my YouTube channel. Today we will learn about offset voltage of operational amplifier. The topics covered in this video are: what is offset voltage, why offset voltage appears in op-amp, what are input and output offset voltages, effects of input offset voltage on feedback circuits, gain versus input offset voltage effect on feedback circuits, op-amp offset null, how change in temperature causes offset voltage drift. What is offset voltage? Op-amp is a differential amplifier. It amplifies the difference between its two input signals. If we explore the internal circuit of op-amp, the first stage is a differential amplifier stage. The differential amplifier of op-amp has been based on assumptions that the transistors are perfectly matched. That means they have exactly same electrical characteristics. But in practical, this cannot be happen because there will be always some differences between the characteristics of these two transistors. So there is an imbalance in the differential amplifier stage. The mismatch in differential amplifier stage is mainly because of four reasons: the differences found in the values of VBE of the both transistors, difference in collector currents of transistors, mismatch in current gain or beta of both the transistors. The emitter and collector resistors values may also differ. These reasons causes one of the transistor to conduct harder than the other. And this leads us to parameters of the op-amp: output offset voltage and input offset voltage. Output offset voltage. When we apply a 0 volts or both input terminals of op-amp is grounded, ideally the Vout is also 0. But in practical condition, Vout is not 0. There is some measurable voltage at the output. This voltage is because of imbalance in differential amplifier. This voltage is called output offset voltage. However, in most op-amps, this imbalance will drive their output to a saturated level, either negative or positive. So, we must eliminate this output offset voltage. Otherwise, this offset voltage will create a problem in later stages of operational amplifier circuits. There are several methods that may be used to eliminate this output offset voltage. One of these is to apply a voltage between input terminals so as to make output 0. As we know, Vout is equal to gain into Vin. Input offset voltage is equal to output offset voltage divided by gain. By using this formula, we can calculate input and output offset voltages for an op-amp. The datasheet of an op-amp shows three important parameters: input offset voltage, input offset current, and input bias current. Here the table shows input offset voltage ranges of some general purpose op-amps and high precision op-amps. The general purpose op-amps input offset voltage is in few millivolts. High precision op-amps input offset voltage is in the range of few microvolts. But it is very hard to predict the polarity of input offset voltage. Two op-amps which are manufactured by same wafer may also have different offset voltages. So the manufacturer provides maximum and minimum offset voltage ranges for an op-amp in its datasheet. Now we will discuss effects of input offset voltage on feedback circuits. Here the diagram shows operational amplifier as inverting amplifier. We must apply a input offset voltage between both input terminals to make Vout 0. Otherwise there is an error in output. So let's discuss this with one example. First we will observe gain versus input offset voltage effect on feedback circuits. Let's take an LM741 op-amp and configure it as non-inverting amplifier. The typical value of input offset voltage of LM741 is 1 millivolt. To make Vout 0 volt. As we know, output offset voltage is equal to gain into input offset voltage. Here formula for non-inverting gain, A is equal to 1 plus Rf by Rin. Suppose Rf is equal to 9 kilo ohm, Rn is equal to 1 kilo ohm, then the gain is equal to 1 plus 9 kilo ohm by 1 kilo ohm. That gives a value of 10 as a gain of this non-inverting amplifier. So output offset voltage is equal to 1 plus Rf by Rn into input offset voltage. Here input offset voltage is equal to 1 millivolt and gain is equal to 10. then the output offset voltage is equal to 1 millivolt input offset voltage into gain 10. That comes 10 millivolt as output offset voltage. Suppose if we apply an input voltage 10 millivolt, then our output voltage Vout is equal to 10 millivolt into gain 10. That comes 100 millivolt as output voltage. We know the error of output offset voltage is equal to plus or minus 10 millivolt. This plus or minus because it is very hard to predict the polarity of offset voltage. So Vout is equal to 100 millivolt plus or minus 10 millivolt. That is either 90 millivolt or 110 millivolt as an output. So offset voltage is a function of DC gain of feedback circuit. Hence, if we increase the DC gain by feedback circuit, error in the output voltage will also increases. It is very important that this error must be very low when we are dealing with very small input voltages. Suppose whenever we are using op-amp in digital to analog conversion circuits, instrumentation and sensor signal amplification, then it is very important that this error in output must be as small as possible. Then we must use very high precision op-amps like AD8551 with input offset voltage as minimum as 1 microvolt. Let's observe the error in output voltage now. Here also non-inverting configuration. So our gain is equal to 1 plus RF by Rin. That comes 10 as earlier. Op-amp AD8551 input offset voltage VIO is equal to 1 microvolt and gain is 10. So output offset voltage is equal to 1 microvolt into 10. That comes 10 microvolt as output offset voltage. Here also we have applied input voltage 10 millivolt. Then Vout is equal to 10 millivolt into gain 10. That comes 100 millivolt as output. We know the error is plus or minus 10 microvolt. So error in output voltage Vout is equal to 100 millivolt plus or minus 10 microvolt. Then our output voltage is either 99.99 millivolt or 100.01 millivolt. Hence from this example, we know that by using op-amp with low value of input offset voltage, error in the output voltage will also get reduced. Here we have used op-amp AD8551 instead of LM741. Error in output voltage gets reduced by 1000 times. The other method to reduce input offset voltage is by using offset null circuits. There are usually provisions made by the manufacturer to trim the offset voltage. Usually 2 extra terminals on the op-amp package are reserved for offset null pins. On a single op-amp such as LM741 and 3130, the offset null connection points are pin number 1 and 5 on the 8-pin tip package. The offset null adjustment requires a potentiometer with its wiper connected to the negative supply or 0 volts of the operational amplifier. It is necessary to check the datasheet for this. The value of this potentiometer may be around 10 kilo ohm to 100 kilo ohm. We must understand the circuit design and also check the datasheet for the most suitable value. Now we will discuss the relationship between temperature and offset voltage. Offset voltage changes with the change in ambient temperature. Here we can represent change in offset voltage delta VOS divided by change in temperature delta T. Data sheet shows this relationship as offset voltage drift. Its unit is microvolt per degree centigrade. Offset voltage drift may be of concern because even with an offset null capability, offset voltage could grow with the temperature changes. For the general purpose op-amp, offset voltage dips in the range of 10 microvolt to 20 microvolt per degree centigrade. For very high precision op-amps, offset voltage drift is used to be in the range of 1 microvolt or 0.1 microvolt per degree centigrade. Now let's understand this offset voltage drift with one example. Let's configure op-amp LM741 as a non-inverting amplifier. RF is equal to 9 kilo ohm, Rn is equal to 1 kilo ohm and apply a input Vin is equal to 20 millivolt. LM741's offset voltage drift delta VIO by delta T is equal to 10 microvolt per degree centigrade. Suppose at 25 degree centigrade we have carried nulling of DC offset voltage. Now we have to find out the error in output voltage at 75 degree centigrade because of offset voltage drift. Here our non-inverting gain A is equal to 1 plus R by Rin. 1 plus 9 kilo ohm by 1 kilo ohm is equal to 10 as a gain. V out is equal to gain into V in. Gain 10 into 20 millivolt input, that comes V out as 200 millivolt. At 25 degree centigrade, we don't have any error in this output voltage because we have already carried out DC offset null at this temperature. Now let's calculate drift at 75 degrees centigrade. Change in temperature delta T is equal to 75 degrees centigrade minus 25 degrees centigrade, that is equal to 50 degrees centigrade. As we know, offset voltage drift is equal to change in offset voltage delta VIO divided by change in temperature is equal to 50 degrees centigrade, that is equal to 10 microvolt per centigrade. So change in offset voltage delta VIO is equal to change in temperature 50 degrees centigrade into offset voltage drift 10, that comes 500 microvolt. Output offset voltage drift 500 microvolt into gain 10, that comes 5 millivolt error at output. Total output voltage after offset voltage drift Vt is equal to 200 millivolt plus or minus 5 millivolt error. Here also plus or minus because it is very hard to predict the polarity of this error. We get output voltage 195 millivolt or 205 millivolt at 75 degrees centigrade. That's all about offset voltage of op-amp and their calculations. So if you have any doubts or suggestions, please mention them in the comment section below. Thanks for watching this video. If you learned from this video, please click the like button. Help others to learn by sharing this video. Please subscribe my YouTube channel and turn on notifications for more such videos. Follow me on my next video, input offset current and input bias current of operational amplifier. Have a nice day.